E658, lecture 5. So yesterday we started looking at circuits that can accomplish the sampling operation. The simplest thing we thought of was take some kind of switch which is controlled by a clock signal, say like this. So when the clock is high, the switch is closed, the input voltage Vin of T appears across the capacitor. When the clock goes low, the switch opens and a charge corresponding to the input at the time when the switch goes low is held on the capacitor until the clock goes up again. We are not quite satisfied with saying we need an ideal switch. So the next thing is, what do we do with the switch? And option is to use an NMOS transistor with the understanding that when the gate voltage is pulled sufficiently high, then the transistor behaves like a closed switch, okay, and when the gate is too low, the transistor behaves like an open switch. So the first candidate sample and hold that we will talk about is the NMOS switch. So this goes to the clock, often denoted by the symbol phi. This is Vin of T, and this is the capacitance C. C is often called the hold capacitance for obvious reasons. When and the sampling clock is denoted by phi. We assume that all the voltage levels on the chip are between 0 and VDD. So under normal circumstances, you would expect that all node potentials inside the chip would be something between 0 and VDD. Okay, so the clock waveform is typically, one candidate for the clock waveform is this character here, which goes all the way from, so this is the time axis, this is the voltage axis, so the clock waveform goes all the way from 0 to VDD. So this is the clock waveform. When the clock is high, this potential is at VDD, this is Vin, alright, and this is the sampling capacitor C. So this is when during the track phase or the sampling phase, okay, these are the track phase, obviously makes sense because during that time the output of the sample and hold, which is this node, is tracking the input. You can call it the sampling phase, so these terms are used interchangeably. If this has got a size W by L, and the usual assumptions are mu n, Cox and Vt and all this other stuff, what is the resistance of the switch? So the equivalent circuit is, you have a resistor, you have a capacitor, alright, and this is Vin. The resistance of the switch is what now? 1 by mu n Cox, W by L. Yeah, what is VGS? VGS is nothing but VDD minus Vn. The source, please note that this is the source, it's in the linear region, right? So hopefully, if Vn is a constant, for example, then the capacitor doesn't draw any current at all, which means that the source and drain potentials must be the same. If this is working well, you would expect the two ends of the switch to be very close in potential, which is equivalent to saying that the transistor is operating well in triode, in which case, whether you assume that the left is the source, or the right is the source, hardly makes any difference. So the resistance of the switch is VDD minus Vn, which corresponds to VGS minus Vt. Okay. Please note that Vt itself is not a constant. The Vt depends on the source body voltage of the transistor, alright, and the body is connected to ground as we discussed yesterday. So the threshold itself also varies as a function of the input. You understand? what can you expect for the resistance of the switch as the input keeps going up? Yeah, of course, we all agree it keeps changing. Okay, can you give me some more intuition? The resistance goes on increasing. First, it's a double whammy because on one side the gate is fixed to VDD, the source is moving up, so VGS is reducing, so VGS minus VT is reducing, and to make matters worse, VT itself is increasing. So the resistance of the switch goes on increasing with the signal. So what is what happens when the input becomes regardless of how high the input is, or is there a limit on the input? So clearly, if the input, if Vin becomes greater than VDD minus VT, the transistor, let me call that M1 will not turn on at all. So clearly that's not a good situation. All of you understand? You ideally wanted the switch to become, a short circuit when the gate terminal was pushed to VDD. However, because of the way the device operates, if the input happens to be greater than VDD minus VT, even when the gate is turned on to VDD, the switch doesn't close. So there is no connection between the input and the output. In other words, sampling is not happening. So already we have seen that the simplest circuit you can come up with has got some problems. If there were no problems, then you move on with life, right? Okay. So one problem is that if Vin is greater than VDD minus VT, M1 will not turn on at all, which is indeed something that we need to fix, because that restricts the amplitude of the signal that you can put in. Okay. What happens when Vin goes low? So what happens when Vin goes low? Is there a problem or is there no problem? There is no problem because the resistance of the switch becomes smaller and smaller. So on the lower side there is no issue with Vin. On the higher side there is definitely a limit imposed by the NMOS transistor because it simply doesn't turn on. Now this resistance changes with Vin. Okay. So can you guys figure out a more fundamental problem? I mean, of course, it is true that if Vin becomes too large, you're screwed completely. Now the question is, okay, if Vin wasn't as large, yeah, sure. I mean, so what he's finding out is as approaches VDD minus VT, the R becomes very, very large. So the equivalent bandwidth of this low pass filter becomes smaller and smaller. Is that clear? As far as the input is concerned, when the switch is on, it just sees an RC low pass filter. So the voltage across this capacitor is a low pass filtered version of the voltage Vin. Now, if Vin is not as large as VDD minus VT, but say significantly smaller, do you still see a problem with it, or it's not a problem? What happens when the input is changing, for example? It cannot follow input, right? So because of the finite resistance of the switch, there will be some finite bandwidth associated with the sampling operation. That's fine. You could make the argument that, hey, I know that my resistance of the switch depends on W by L. If the resistance is too large, then the bandwidth falls. So I'll fix that by using a larger transistor, a larger W by L. That should reduce my resistance, thereby increasing bandwidth. So is there a problem with this, or the resistance of this guy depends on the input? So what is happening? Is this a linear system or a non-linear system? The resistance depends on the input. So this is clearly, I mean, in very, very loose, inaccurate terms, you see that the pole of the system is moving along with the input. The whole notion of poles and zeros only works when things are linear. But so clearly when the so-called poles start moving with the input, things are absolutely non-linear. So intuitively you can see that if the input was a sine wave like this, so let me call this say VDD by 2, and there is a sinusoidal input riding over VDD by 2, then what can you, the output should in principle follow the input. If the bandwidth is sufficiently high, the output should follow the input as long as the switch is turned on. But now what is happening when the input goes high? What happens to the bandwidth of the RC network? Reduces. So if the bandwidth of the network reduces, what can you conclude? Let me refresh your memory on RC circuits. So if this was an ideal RC, I mean it's a linear R and a linear C. If the bandwidth is much larger than the signal and signal frequency, and this was the input signal, what can you conclude about the voltage across the capacitor? It will also be a sine wave. Can you comment on the magnitude of the gain is approximately 1. Okay, so in other words, I am saying that the frequency of the input sinusoid is much smaller than the bandwidth. So the magnitude response is almost 1. What can you say about the phase? At DC it is 0, but what will you, I mean, okay, so the output sinusoid is lagging the input sinusoid. Alright, so I mean, so can you comment on this delay for the output sinusoid? So when it's lower, you would expect the tracking to be quite good. For example, say like this. Okay. The moment the input starts going up, the delay starts to become larger. And the same thing here, and okay, you probably see something like this is a nonlinear effect. Everybody understands that, right? For dynamic signals, there is distortion. And this is harmonic distortion because the input is a clean sine wave and the output certainly doesn't look like a sine wave because different parts of the sine wave have been delayed by different amounts. Okay. So distortion is something you should expect. You do, and this is coming because of the dependence of R on Vn. And please note that I am considering Vn well within that range before the switch gets. So clearly there is an issue with this thing. So the next idea is to say, hey, maybe NMOS was a bad idea. Perhaps we should try a PMOS transistor. You know that when you have a PMOS transistor, what happens? So let me try a PMOS device. So if this, earlier we had used this waveform like this, and this was called phi. So an NMOS transistor is on when the gate is pulled very high. A PMOS transistor on the other hand is on when the gate is pulled to the lowest potential you have, which is ground. So instead of using, if you want to still sample during when phi is high and hold when phi is low, what you should do is connect the gate of the PMOS transistor to not phi but to phi complement of phi bar. You know, a little bit of thought will show you that you will inherit most of the problems that you have with the NMOS transistor, like, you know, switch resistance depending on the input and all this other stuff. However, the only difference is that the PMOS likes things when the input becomes high, alright, and doesn't like it when if Vn becomes too low. What happens if in fact if the input voltage attempts to go below a threshold of the PMOS transistor, then the source gate voltage is not large enough, so the PMOS transistor will not turn on, thereby disconnecting the input from the switch. Is that clear? The problem with this is that When the inputs become too small, this doesn't work. So, what is the obvious conclusion? How can you make things? So, NMOS has got a problem when things go high, PMOS has got a problem when things go low. So, the obvious thing is to put both of them together and make a transmission gate. Put both of them together so that if you plot, for example, the conductance of the NMOS transistor as a function of voltage. So, let us say the input is, the x-axis is voltage, is Vn, and it varies from 0 to VDD. Can you comment on the conductance of the NMOS transistor as the input varies from 0 to VDD? The conductance of the NMOS transistor keeps falling because the overdrive is the largest when the input is, for an NMOS transistor, VGS minus VT is the largest when VGS is the largest, and that happens when the input is 0. So, the conductance of the NMOS transistor does something like this. In fact, this distance is VTN. And what can you comment about the conductance of the PMOS transistor? It should do the opposite thing. So, this is the conductance of the NMOS device. This is the conductance of the PMOS device. The total conductance of the switch, therefore, is the sum of the two conductances. So, it probably does something like. So, this is the switch conductance. And you can still see that the switch conductance depends on, you have avoided the problem of not being able to use too low or too high an input voltage, that's all. But the switch conductance definitely depends on the input. So, even though you probably avoided to some degree mitigated the distortion that could occur when the input changes, but you should definitely expect to still see harmonic distortion when the input changes, simply because the resistance of the switch is being modulated by the input. So, this is a vague attempt at making things work reasonably okay. So, before we get into the non-idealities in the hold phase, let us kind of quickly evaluate what kind of distortion numbers we can expect when you have a sample and hold like this. Okay, so in other words, this is a nonlinear resistor. This is the sampling capacitor. So, this represents the equivalent circuit. So, this is Vn. Of let me say track and hold in the sampling phase or in the track phase. Okay. And clearly, I want to emphasize the fact that the resistance depends on the input voltage. If Vin was some VDD plus VDD by 2 plus A, say cos omega t, I'd like all nonlinear systems, I'd like to figure out, I put in a sine wave, and if the system was absolutely linear, then if I looked at the voltage across the capacitor, it should also be if R wasn't dependent on Vin, then can you comment on what would happen when I put a sine wave at the input? The voltage across the capacitor will definitely be shifted in phase from the input, but it would be a pure sine wave without any harmonic components, right? Because of the resistance depending on Vn, what would you expect? you will see harmonics, and an index of how good the so-called, how close to linear the sample and hold is the amplitude of the harmonics relative to the fundamental. That sounds like a reasonable definition. Okay, so obviously, if you write the differential equation here, it will result in a what kind of differential equation? There's one energy storage element, so if you write Kirchhoff's laws, it will be a differential equation. Clearly, it will be a first order nonlinear equation. Okay, omega and r of Vn, etc. influence the distortion. Is that fair? So to that end, I will assume that V out so this is estimating distortion due to the switch the key assumption I will make is that the bandwidth in the track phase is much higher than input signal frequency. So what does this mean? If the bandwidth of this RC network is much larger than the input frequency, can you comment on the voltage across this with respect to the voltage across the capacitor? So this assumption is true, then I can approximate the voltage across the capacitor to be, okay, before we get into the math, let's spend a couple of minutes getting intuition about what we should expect. So why do you think there would be distortion at all? There's some nonlinearity. Okay, so can you comment on what the distortion would be if omega was 0? There will be no distortion. Why? At DC there is no distortion in spite of the resistor being nonlinear. I mean, when you're talking about, when I say DC there's no distortion, I mean the DC is like within quotes, it's not a sinusoid, right? So when I say DC, you would expect that for very low frequencies there would be no distortion, simply because even though the resistor is nonlinear, as the frequency tends to 0, the displacement current in the capacitor is 0, because the current through the capacitor is C dV dt, correct? So, and the output voltage sitting on the capacitor is nothing but the input voltage minus the drop across this resistor. If there is no current through the resistor, then regardless of how nonlinear the resistor is, there is no voltage drop across the resistor, which means that the output and the input must be pretty much identical. So the culprit therefore is the current flowing through the resistor. So based on this intuition, what can you expect as you increase frequency? Will it get worse or will it get better? The distortion of the sample and hold, okay, the tracking during the tracking phase must get worse as the input frequency increases. You understand? Because as the input frequency increases, C dV dt increases, which causes more current to flow through the nonlinear resistor, which causes more distortion. Is that, we'll prove that a little later on, but intuitively this is what you must expect. What about with amplitude? Do you think things will get better or worse? If I increase the amplitude, there's the frequency of the sinusoid and there's the amplitude of the sinusoid. So, do you think the distortion products, the harmonics will increase when the input amplitude is small or when it's large? That's obvious, right? So, any nonlinear system, things always tend to get, generally things, nonlinear devices, circuits produce more distortion for larger input amplitudes. Okay, so it's definitely true that there are some exceptions. Okay, generally this is what you can expect. We are interested in calculating distortion. So this is V out. and let me call this say Vx. Clearly V out is nothing but V in minus Vx. So if we make the assumption that the bandwidth in the track phase is much larger than the input signal frequency, it just means that the voltage drop across the switch is much smaller. So to first degree you can approximate the current in the capacitor. So the IC of T is nothing but C dV out by dt, which is approximately equal to C dV in by. And please note that typically, you expect systems to this distortions of 1% and 2% and so on, which may seem like small numbers, are already too big for a whole bunch of practical circuits. So if you want any reasonable amount of precision, you're always looking at distortions numbers of the levels of 0.1% and so on. So while it is under most practical situations, this assumption will be valid. So C dV out by dt can be approximated to be C dV in by dt. Okay, and what is this now? C times A omega so that's the approximate current flowing through the capacitor, and this current goes through the resistor and creates a drop. If this was a linear resistor, the drop would also be purely sinusoidal, and when you subtract two sinusoids, you still get a sinusoid, so the output will be devoid of any harmonic components. However, now the resistor has got nonlinearity in the sense that it depends on the input. So when this sinusoidal current goes through a nonlinear element, it will produce sinusoids at frequencies other than the fundamental. And since the output voltage is simply the input voltage which has got only one frequency component, okay, and Vx which has got frequency components at multiples of the fundamental component. The distortion in the output is simply gotten by looking at for example, the second harmonic component in the output must be the same as the second harmonic component in Vx. The third harmonic component in the output is the same as the third harmonic component in Vx, simply because Vn is a pure sinusoid. Clear? So now let's quickly go and calculate Vx. So now the question is find Vx. And we said that this R, resistance of the switch, is a function of V in, and we have seen three candidates. One is just the NMOS switch, one is just the PMOS switch, and one is the CMOS switch. And for each of these switches, you have different ways in which the resistance of the switch varies with. So a safe way to go about things is to just say that depending on the way the switch is implemented, this R0, R1, R2, etc. will vary. If you had a perfectly linear resistor, then what you would think would happen to R1, R2, etc. would all be 0. Okay, straightforward. So what is Vx now? Vx is nothing but the current minus AC omega sin omega t times R0 plus R1, and what is Vn? A cos omega t plus R2 A cos omega t the whole square, so which is nothing but minus A C R omega sin omega t minus A C R1 omega sin omega t cos omega t. This must be A square C R1 omega sin omega t cos omega t. Please note that there is one A here and there is another A here. Similarly, it must be the cubic term should be A cube C R2 omega times sin omega t cos square omega. Okay. Please notice that in the absence of distortion you would have only the first term, which is equivalent to saying that if you put a cos omega t sinusoid at the input, the output will be this cos omega t minus a sinusoid which is 90 degrees out of phase, and the magnitude of this sinusoid is very small for small frequencies, which is equivalent to saying that the output sinusoid is not in phase with the input. This is stuff that you already know. For small omega, clearly the bandwidth of the track and hold is basically about 1 over RC. Okay. The argument that the input frequency is much smaller than the bandwidth basically means that we can kind of neglect this term. In any case, this frequency is at omega itself, which is equivalent to saying that the fundamental component at the output is almost the same as the input fundamental component, which you knew already. The fundamental component at the output is the fundamental component at the input minus this ARC omega added properly in the right phase. Now for low frequencies, we said that the assumption we make is that the input frequency omega is much smaller than the bandwidth of the track and hold, which is basically means that omega RC is much smaller than 1. The output is virtually the same as the magnitude of the input sinusoid. So what about this? So the fundamental at the output is nothing but the component at omega is nothing but A. What is the component at 2 omega? It's A square C R1 omega by 2. And what is the component at 3 omega? A cube C R2 omega times, now I need some way to help me out with this math. So it is what? By 2 times, let me just simplify this. So sin omega t cos square omega t is 1 plus cos 2 omega t by 2. This is 1 plus cos 2 omega t by 2, and when I multiply this chap with this chap, I need to have another factor of 2 to get to the A cube C R2 omega by 4. And as we expect, the distortion terms are dependent on frequency. With the larger frequency, you get more distortion. With a larger amplitude, you get more distortion. The component of the second harmonic depending on A square and the third harmonic being dependent on A cube is something fundamental to all nonlinear networks. The second harmonic is coming from the square, alright? And what is squaring? It is taking the signal and multiplying it with itself. So any component at 2 omega will result from the input somehow getting multiplied with itself. And when you multiply, and the input has got an amplitude A, so when you multiply it with itself, the strength of that component has to be proportional to A square, which is intuitively why second harmonic always depends on A square. Similarly, the third harmonic distortion will also always depend on A cube, because you are multiplying the input with itself and with itself again. So A times A times A gives you A cube. And in this situation, it also happens that the the distortion also depends on the frequency, simply because the displacement current through the capacitor is directly proportional to. The bottom line is that for a sample and hold like this, where the switch got a resistance which depends with the input signal, the voltage across the capacitor has not only got the input sinusoid but components at multiples of the sinusoid. And the moment you open the switch, what do you think you've done? I mean, this is in the track phase, you want to hold it, so you want to open the switch. Okay? So when you open the switch, what do you think happens? The voltage across the switch has got frequency components which are, if the switch was not non-linear, you had a linear switch with a constant resistance which didn't depend on the input. The voltage across the capacitor is a pure sinusoid, and when you open the switch, you have now on the capacitor some charge, and if you plot the charge on the capacitor as a function of time, you get a discrete time sequence where the frequency content of the discrete time discrete time sequence simply corresponds to the input frequency and when it's sampled. All right. Now, when you have a nonlinear switch, the continuous time voltage waveform across the capacitor has got not only input frequency but its harmonics. So when you open the switch, the charge trapped on this capacitor forms a sequence. If I do this, for the first clock cycle, second clock cycle, and so on. So this discrete time sequence, when you look at it in the frequency domain, what all frequency components do you expect? You will expect to see frequency components not only of the fundamental frequency but all its harmonics. And please note that once the in principle, when a continuous time sine wave when passed through a nonlinear network has got all frequency components. But when you sample those frequency components, what happens? They will all alias back. So you will expect to see a whole bunch of tones. For example, let's say you are sampling a 30 kilohertz sine wave at 100 kilohertz, and there is some distortion in your sampling circuit. So it will produce 60 kilohertz as well as 90 kilohertz. 60 kilohertz when sampled at 100 kilohertz will look like 40 kilohertz. 90 kilohertz when sampled at 100 kilohertz will look like 10 kilohertz. Okay. So while in the continuous time spectrum, if you put a sine wave here, you are expecting to see distortion products here and only in a monotonically increasing sequence. When you sample that spectrum, you can expect to see the fundamental. For example, when you sample a discrete time, do you follow what I am saying? So in continuous time, if you put in a sine wave here, you expect to see distortion components. This is the fundamental. You expect to see some distortion components here, and some multiples like this. Okay. Whereas when you sample this waveform, it is not at all inconceivable that this is the fundamental. This could be the second harmonic. This could be the third harmonic, and so on. You can't expect all these tones to fall off. So interpreting so by analogy, interpreting the harmonic content of an A to D converter requires some, a little bit of care, in the sense that the harmonics will not occur all at multiples of the input frequency. Because once you sample them, all these harmonics will alias into different frequencies. Okay, so I think I'll stop here. We'll continue tomorrow.